Hello, everyone. Thank you for joining us. We are starting our webinar today. Our subject is tuning level controllers for surge tanks, standpipes, and more. I'm Vera from Control Station. I work in the marketing department, and I will be hosting this webinar with Bob Rice from Control Station and Maxime Lachance from BBA today. And just before we start, I want to invite you all to input your questions. Anytime during the session, there is on this panel a tab named questions, and you can write your questions. And in the end of this webinar, Bob and Maxime will be answering them. So our presenters are Bob Rice and Maxime. Bob has over 20 years of engineering and product management experience in process industries. As a recognized leader, Bob oversees development of Control Station's award-winning suite of process diagnostic and optimizations technologies, including Plant ESP, control loop performance monitoring solutions. And Maxime is an automation expert and professional engineer with deep expertise in process control, a dedicated volunteer and industry leader. He drives projects from concept to optimization. His award-winning solutions blend technical excellence with real-world insight, advancing automation through leadership and innovation. For those who are new to Control Station, we've been driving innovation in process control since the 80s. Today, we are proud to support customers all around the world, including many of the leading manufacturers across the process industries. And about BBA, we are also pleased to be joined today by our partner, BBA. We are in collaboration for more than 5-6 years, and they have over 40 years of experience. BBA focused on energy and natural resources industry. They have experts across 20 offices through Canada, US, Chile, and they support key industry like energy, chemicals, mining, and pulp and paper.
Excellent. So thanks everyone for joining me and Maxim today, and we're going to be talking about level control, which is one of the more difficult styles of loops to tune, and hopefully by the end of this webinar they won't seem so difficult and strange. And so we're going to cover kind of a lot of background behind level control. We're going to talk about the different styles of level control objectives, different types of applications, different types of tanks that you may experience. We're going to talk about the process dynamics and how they differ from things like flows and temperatures, and why that makes a difference to the tuning process. And then we're going to talk about some of the tuning strategies that you would employ. So we're going to talk through kind of the model-based approach, some of the pitfalls and challenges, and talk through some different scenarios, different ways of tuning surge tanks and cascade controllers, and just really trying to cover a lot of topics around level control. And it is a very deep topic. Me and Maxim are both going to be checking our watches to make sure we don't extend past our 45 minutes, because I know we both teach classes on this, and this is one of the more challenging topics and more interesting topics. A little bit of a background, like I've been doing process control for a long time, but I actually did in graduate school. My whole PhD is on level control, as sad and silly as that sounds, but that is literally what I studied for 3 years. And it seems like still 80% of all the loops I get asked to tune by customers are level controllers. And quite frankly, I'm kind of sick of tuning level controllers. So if we can, pass on some of these tips, maybe you won't have to call me so much for level control. I'll always take the call, and I'm sure Maxim will always take the call on how to tune them. But hopefully by the end of this, you'll get a little bit more kind of information around how to approach level control. Can you go ahead and pop over to the next survey question here, or the first survey question here? as you're approaching tuning level controllers, how do you do it now, right? Do you not tune any level controllers, which is, it would be a strange webinar for you to join if you don't tune any level controllers? Do you tune by trial and error? Do you apply tuning methods? Do you use software? Are you just new to tuning and want to kind of learn some of the new ideas, right? There's lots of different approaches to level control. There's lots of different theories behind it. We're going to go through kind of the model-based approach. Maxim, when you first started, tuning level controllers, how did you apply it? What was kind of your first process when you started looking at and tuning level loops?
Yeah, if we go way back, I did I think my first level controller by trial and error. So I learned a lot about the process dynamic, but shortly after, I've learned the process that we'll show them today, which is understanding the response of the process by modeling the response and getting the model of the response. And then once you know how it behaves, then you can back calculate your tuning and choose the response that you want based on the type of processes or the control objectives that you want to meet.
Yeah, and that's really the approach, and what's really kind of important is that control objective. And I know me and Maxim are going to talk a lot about control objective and purpose of the level control, because a lot of times that's completely misunderstood.
I wish I did.
Yeah, go ahead, share the results. So about what we'd expect, right? Probably a split even between trial and error and in a tuning method. 20% use tuning software. Hopefully we can get that number up. 2% don't tune PID loops. Again, kind of a strange webinar for you to join, but if you like watching me and Maxim talk through the topics, I get it. So that's excellent. Maxim, you want to go to the next slide, Vera? And
sure. Right. So we'll, as we said, we'll show you how to tune and give you tips about level control tuning, but why it matters, right? So before we get into the types of response that you want, level control will help you in different aspects, right? So there's a first, let's say, a safety components about it. So why safety? Well, you have sometimes, it could be water, but sometimes you have chemicals, you have different processes, and you have tanks, and some of those tanks are even open, right? So if you don't have good and effective level control, what's going to happen to those things? Well, you might spill, you might have overflows, you might have overpressure. So all of this can put you at risk on the safety side, right? So there could be workers underneath. If it's a chemical spill, you can add regulation aspects to it, which maybe need to be reported. If we stay in the safety, well, we have the safety of the people or the environment with good set level control, but you also safety related to your equipment. So we all know pumps cannot run dry. There's an interlock that will stop it, but do you really want to reach the interlock, right? You don't want to stop your processes, have downtime, have to restarts, and then get back on. So safety aspect of it will be one of the things that we consider when we do level controller. And if we go even deeper in the regulation, I talk about environmental permits, spills, and reporting. If you go into a boiler system, which is a highly managed, well, the level controller inside a boiler is something that is critical aspect, and it's really important. It needs to be done. So there's a bunch of other components with the burner management systems that you need to meet, but level control will be one of the aspects. If you have good, reliable, stable control, then of course all the rest will fall in place and help you meet all those regulations and be safe in your aspect. So safety is one, and then we can go into efficiency. So efficiency, we'll see how we choose how to tune our level based on our objective, based on the tank types, based on the types of processes. So what efficiency we will mean different things for different operation, but basically we want to make the process stable. We want to maximize our throughput. We want to reduce our disturbance. We want to prevent any downtimes. And if we have good, effective control, then we might see effect on our energy usage. So if we're swinging and our pumps are more stable, energy savings is one, it could be one aspect. And if we go, we talk about level control that are done with valves and regulating valves. Well, wear and tear is one aspect, right? So sometimes you may have, let's say, really tight control around your level, if that's your objective, but then you look at your control elements and the valve keeps on moving from 20 to 80, and it's working way too hard basically to keep you tight. So what that does, well, it's not really efficient. So we'll have wear and tear on your valve, and then you can reach the point where maintenance, it's more costly, and replacement, downtime. So basically you're not really efficient. So it's really a balance of your equipment, your types of process, and your need, and we'll show you different types of processes and different types of condition. And now when we talk about, let's say, stability, it's kind of mixed with the efficiency. So what is stable for you? Well, it will depend on the type of application. So if you have like a buffer tank, you want to make sure that you're never empty, right? Your product is available when you need to draw it from your types of processes. If you have a contact tank, and the contact time will be important, so level control will play a role in those. Chemical plant, let's say pH control or water treatment plants. And stability may not always mean stable level control. Sometimes we will use those tanks, as you'll see, as to absorb the disturbance, to absorb the variation. So every time there's a process upset, those tanks can absorb this, so the level will go up or down. So that's where the variability in your process will be, but the upstream and downstream will remain somewhat stable. So that's why level control matters. And I will pass now back to Bob. So we'll show you different types of process.
So Vera, can you pop to the next slide? And so, because you have all these different kind of contributing factors towards level control, you have a lot of different control objectives and purposes behind the level control. And, you kind of think about maybe like a flow loop. A flow loop generally always has the same objective: track target. You give it a set point, you want to follow that target, and generally nice and smooth, but it has a singular purpose. Level control, the objectives are all over the place. They can be to absorb disturbances. And so you're less concerned with a tight set point, and you actually allow that process variable to move to try to disconnect incompatible flow patterns, right? So if you've got an oscillation here, you put a tank in the middle, and that tank is going to absorb the oscillations so they don't get transmitted downstream. There's a different control objective for something like that versus something that's designed to supply a constant head pressure on filler machines and stuff like that, where you need to be ultra precise with the level control that you have. And so you have to think through what the control objective is, right? And the control objective is going to vary dramatically based off of what the purposes are. What's the safety considerations? What's the stability requirements? What are the efficiency requirements? And so you have to think through what the purpose of that level controller is. It's not always super tight set point tracking. In general, some of them can be that way, some that can actually be counterproductive to the actual overall control of the process, right? And so if you tune every single level controller in your entire facility to be incredibly fast and super tight, odds are you're going to introduce more disturbances into the system than what you had before. And so a lot of times it's just that misunderstanding of what the purpose of that level controller is, right? Level control, you need to think through the objective. And if you sat through some of our other webinars about the tuning process, the very first step is defining that control objective. What is the purpose? What is the need of that process? What is it supposed to do? And so as you think through the different control objectives, think through what that process is supposed to do. Is it supposed to supply a very constant head pressure, so the system fills appropriately? Is it supposed to suppress disturbances? Is it supposed to decouple flow oscillations with the surge tank in the middle? Is it designed for phase separation, where you've got materials and circuits that are trying to basically cut a different phase in the fluids across a weir or something like that? All those are different applications and different objectives, and you need to think through what those are, right? And so Maxim's going to talk now a little bit about those kind of different processes themselves. We talked a little bit about the objectives. What kind of processes are those?
Yeah, thank you, Bob. So if you're responsible for tuning the loop, right? So Bob explained that there's different types of processes. So your role will be to decide, well, what do I need to do? and we'll show you how to pick the tuning. And basically there's different types of response, okay? So you may want to have what we call a fast response. So you can say like it's aggressive tuning. So what it will do, so if you have those types of tunings, you will go faster to set point, and if there's a disturbance, you will reject it fast, right? We seem to think that fast is always good, but it may not be. Fast example of control that needs to be fast. Let's say you have a standpipe, water, header distribution, flotation cell. You want to be fast. You want to be fast. Why? So let's say a water distribution header, right? There's many clients that's looking at this level, or that's drying water from, or product from that controller. So if the level change, we have change in pressure, then everybody is affected. So those needs to have what we call fast response to be able to be stable, so all the clients don't see any changes, right? And they're not affected by each other. So if one draws a lot, the other one is not affected because the main one, the level is stable and you're fast. So fast response is good. If we talk about a flotation cell, so in the mining, if you're not familiar with mining industry, we have what we call flotation cells. So basically, we grind all the rocks very, very small, and then we send that in what flotating cell where there's water, air coming up with chemicals, and it makes bubbles. And the chemical process is that the metal that you want sticks to the bubble, goes onto the surface, right? So there's kind of a froth that floats in the flotating cells. So the level is really important because we will extract only the part that's floating with the material that we want. If we don't have good level control, then if it goes up, then we will carry unwanted materials downstream our process. So that's not what we want. So this is an example where we want stable, steady. So we want a fast response. If there's a disturbance, we don't want to send this way. We want to kill it right away. So that's the what we call a fast response. Sometimes speed is not our friend, right? Sometimes we want what we call detune and have a slower response, right? We don't want to be aggressive. And what type of application we could have? So imagine a surge tank, either in a chemical plants or a brewery, right? That it takes the excess material coming into the surge tanks, and then we need to release it back, right? So of course, my goal is ultimately is to keep the surge tank empty and empty it. But I don't want to do it fast, right? It comes in, I don't want to send it back in the process as fast as it gets in. Why? But because I'm sending a wave downstream, I'm affecting whoever's my client is downstream, and we don't want to send those disturbances. So this is a type where we will have a slow response, right? So we absorb the surge, but then we release it slowly. So as the one responsible to choosing the control, I need to be aware of that and say, you know what, my response will be slow. It's okay if it goes up. It's meant for that. I will just discharge it slowly with minimal impact downstream. And sometimes it's a mix in between, so we have to account what's coming in upstream, what's going on downstream, and I call it's a kind of a, let's take a buffer tank in between two processes. So once sending it to my tank, and then I'm sending it downstream for my downstream client and my downstream process, right? So as the inflow and outflow change, I will have unbalance, right? So these tanks will go up or down. So my goal in here is not to maintain the steady level, is really to absorb the variation in my processes. Let it go up, let it go down within a certain range. So we have what we call like an averaging controller. We'll say we'll go from 80 to 20% to 80. Let's say, for example, that's the margin that I'm allowing my tanks to swing, so whatever the number it is. So in this case, this will be kind of a balance, and my goal will be to absorb those variation and minimize my impact downstream and upstream, and kind of balancing. And sometimes it's a mix of many objectives. So I will give again an example in the mining industries. So we grind the rocks, right, in small parts, and then after the grinding circuit, it goes back into a big bump off, kind of a buffer tank. So the rocks falls in it, and then I'm pumping it downstream, right? So of course I need to maintain the level in that box, but there's other objectives that may come in play, right? So the box, I want to pump it out, but I'm pumping it out sometimes to a classifier. It's a cyclone. Whatever the process is, it needs stable pressure. So I have my pump box. I'm pushing it out, but I'm looking at my pressure. But at the same time, I'm looking at my density. So I'm adding water to the rocks to meet a certain mix. So I have density, I may have pressure, and at the same time, I don't want to lose my level. I don't want to add too much water. So it becomes a balancing. So all of those aspects, you'll be the one responsible to understand the different dynamics and choose, do I need to be fast? Do I need to be slow? Do I need to use it as a disturbance kind of absorbance, or do I need to integrate it into a larger scheme? And we will show you based on those objectives how to pick the response that you want and choose your tuning accordingly.
Excellent.
That's
Excellent.
pass it forward.
Yeah, it's so many different types of objectives, right? And that's really the challenge with level control, is if you try to treat it as like the same objective every time, a broken clock may be right twice a day, but you're still going to mess up a lot of processes, right? So you really think through what the control objective is. Vera, can you flip to the next slide? So just a quick promotion for next month, we're going to be talking with Tim Shope, who's an industry leader at Hargrove Controls and Automation, talking about state-based performance and state-based analytics, trying to understand how process conditions change and how you can apply controller performance and monitoring to applications where it's not running the same type of process all the time, different grades, startup, product transitions, testing, different types of scenarios, and how do you actually account for that from a controller performance standpoint. And so that'll be next month in July. Excellent. So next slide. And we've got the survey, right? So when you're thinking about your level application, what are some of the biggest challenges that you're trying to work through, right? What are the different types of application issues that you have? Is it oscillations and instability? Is it your level controllers are too slow and are not responding? Are there safety and overflow? Do you have a lot of valve and instrumentation issues where your level equipment isn't, being able to sense the level appropriately? Do you have the right technology in place? Do you just not have the time and experience or tools maybe to approach level control from a more systematic approach? Kind of what is the biggest issue that you see? From my standpoint, it's always the first one, oscillations and instability. And I'm sure probably Maxim has kind of a similar explanation, but for me, when I go into a plant and I do an audit, if I want to find quick wins, I just pull up every single level loop, and odds are 10% of them, 20% of them are oscillating to a degree that makes everything around it unstable and causes issues. So if you want some quick wins, pull up your level loops, find the ones that are oscillating and go and fix them, right? They're always kind of the ones at the beginning there.
Yeah, I may add, Bob, like the oscillation sometimes is in the level itself. So you will see the level fluctuate, but sometimes that's what we want. So what I see is the oscillation is sent downstream. So the level is super tight, but all the inflows coming in it's sending oscillatory downstream. So it's even worse now because all the processes downstream are affected by basically the level loop. So it's the level, the way the tuning were choose were not appropriate, so it's pushing the oscillation downstream and affecting way more processes than the level itself.
Yeah, absolutely. Again, levels are always kind of a good place to look for the issues. How are we doing on the responses, Vera? Yep. Brilliant. And look at that. It's almost like me and Maxim know what we're talking about, right? Number one issues with level control, oscillations and instability, right? Over half of you said that, and that is not at all a surprise, right? That is where issues crop up, right? And so that's really interesting. And now Maxim and I are going to kind of talk through how to tune this, right? We've talked about the objectives and so forth. So Maxim, you want to talk a little bit about the process dynamics?
Yeah, of course. So we're focusing on level control here. So there's two types of response, right? So imagine like a standard flow loop, right? There's a pump and there's a valve. I open the valve. We call that a self-regulating. Why? Whatever the position it is, I have a steady flow. I move the valve up, the flows increase, and then it restabilizes. We call those self-regulating. There's a lot of processes are self-regulating. When we talk about level control, most of them are called what we call integrating process. Why integrating? So let's imagine there's a tank and I'm adding water to it and then I'm pumping it out. If I add as much as I'm pumping, of course, the level is stable. But let's say I start adding more. like the little graph that we see in the middle. So let's say I'm opening the valve and I'm starting adding more water. I break this balance, right? So what's going to happen? Then the tank will just fill and continue filling as a steady rate. So that's the type of response that we see here with the line, the level going up. So how we deal with that? Well, if you have a self-regulating, we do what we call a first order plus dead time modeling. But in this case, this is not what we will do. We will show you how to model it like the one we see in the middle, and I'll show you in details on the next slide how to do that. But basically, we'll have, oh, you can stay Vera on the first, it's okay for now. I'll get back to this one, I'll show you. So we'll show you how to model the response of an integrating process, and why we want to do the model, because once you know how it responds and how you know the model, then Bob will show you the small tricks and calculation to pick the type of tuning that will meet your tuning criteria. So we will learn all of that, but there is non-linearity, and there's particularly in your process that you need to be aware of, right? So for example, tank geometry. Imagine you're filling out a tank and it's, let's say it's a round shape. So at first, if it's empty, you will add a little bit and then you will see the level goes up. Or imagine if it's a conic shape, right? So the bottom of the part, a little water will increase the level fast, but when you get in the wider part, it needs more water to see the level change. So the response with how much you add or how much you remove will be function of where you are in the tank. So you need to be aware of the tank geometry and account for it. Another non-linearity that you can see is the way the valve is made. So if you have different types of valve, as you're aware, there's different types of response. They're not either fast opening, so they're already, let's say 60, 70% open, but after that, the maximal flow is already reached. Some of them are more linear, which is great. Some of them are equal percent. So the valve characteristic will have a different response depending on where this valve is operated. That's another thing that you be aware, because every time there is the dynamic change, it will affect your tuning. So you need to understand where you want to work and pick the right tuning. How you want to deal with those non-linearity, but there's different ways. So if you stick, let's say, with a valve that has a non-linear behavior, where you can, what we call, characterize that valve. So meaning that based on your PID output, you will send the actual request of opening to have a linear response from your valve. So this is something kind of that you can add to remove the non-linearity from your valve response. Now, if you have like a tank geometry that is changing, there's not much. Of course, you cannot change the tank geometry, but there's a few things. So first, what we say is that depending on where you are, if the response is not too much different, we will say tune for the worst case. So we'll show you how to tune, and what will be the worst case for you is long dead time or high integral gain. So we'll show you both of those. So the idea is that if you take the most difficult portion to tune and you choose your parameters, you will be stable throughout the other one. If you do the reverse and you would pick the parameters where the model or your response is the easy one, so a small gain, a short dead time, you will come up with tuning that are a little bit too aggressive, and then you will change operating position or operating place in your processes, then you may have instabilities. That's why we say take the conservative tune for the work, guys. And if you see that it changed way too much, there is adaptive tuning, meaning like if I'm operating in this portion, I will use those tuning sets, but when I'm here, I will use a separate tuning set. Bob will talk about that. So keep those in mind. We'll talk a little bit about those, but now we'll show you how to model an integrating process response. So it's relatively easy. We're looking for only two things, and with those two things, we will come up with your proportional gain, your integral gain. So the first thing that we want to do is the one we see in the middle with the theta p. So it's the dead time. Dead time is the easy one to know, is like how much after I make my move. So you see the CO is my output. So either I'm pumping more or I'm opening a valve. I can see my response. So after I move, how much time it took for my level to start moving, that's my dead time. Okay, dead time is really important because it giving you basically it sets the speeds of the whole response. So usually you cannot go, there's kind of a rule of thumb that say that you cannot go faster than 10 times the dead time for your stabilization, right? So it's really an important factor that you need to pay attention with your dead time. The second one we want is what we call the integrating gain, which is shown here with KP. So basically, it's easy in this solution. You don't need to be stable, so you make the level go up, and then you make a break, you make it go down, and you compare the second slope minus the slope one divided by the change in your CO. So what it's telling you, but for every, let's say, percent of movement I do in my controller output, how much my level will change, let's say every second or minutes based on the unit time you have. So it's giving you a hint that if I move by 1%, how much it increase or decrease every, let's say, minutes, because in this graphic it says minutes. So if you know how fast it reacts, what's the gain, then you can properly back calculate the tuning as we'll just learn now. So with those two easy numbers, then you can set your tuning. And again, set your tuning how? Well, based on your control objective: slow response, fast response, disturbance rejection, and so on.
Yeah, and so this is really important. Understanding the dynamics sets the stage of what's possible, right? You can't go faster than 10 times your dead time. That's a limitation, and how fast your tank fills or drains is going to also have an influence, right? If you've ever tried to do level control in a tank that's way too small, you know how difficult that is, right? If you're trying to do, you got a 50-gallon tank and it's 50 gallons per minute of flow rate through and out of it, that's not a lot of residence time, right? And so these dynamics kind of set the stage for what is possible, and understanding the dynamics is really what lets you calculate that, right? So go ahead and go to the next slide here, and I want to talk a little bit about objective and trying to determine how fast you should bake your tank, right? And so we talked about control objectives early on. We talked a little bit about, some need to be very fast, some need to be very slow. Well, how do you actually kind of turn that into a number that you can use in the tuning formulas, right? And what I want everyone to start thinking about from a level control perspective is the idea of what is known as an arrest time. It's basically how long does it take for the process variable to basically arrest or stop a disturbance, right? You're running along at set point, everything's good. All of a sudden you get hit with a disturbance, your level starts to drift up, and you have to turn back around to bring the level back. The time it takes to turn is an arrest time. And so how do you think through what the arrest time is for a process? What is appropriate? And so I'm going to go through a very kind of simple kind of mental exercise with the example on the screen here to kind of how you come up with a kind of an acceptable arrest time. And it really, you need to understand the process, right? Which is pretty important for tuning any loop, is understand the process, understand the tanks, understand the flows, kind of understand what's going on with the process. So here I've got a tank it's 100 liters, right? It has 100 liters of liquid. It's a very linear tank, right? So it's pretty simple. Target's at 50%. So there's 50 liters inside the tank. And let's say we have high and low targets that we have to stay within, right? So as long as we're beneath 60% and above 40%, everybody's happy. That means that if I'm sitting at target, I've got about 10 liters above and 10 liters below my target that the level can move safely within, all right? So it's basically kind of the capacity of level that I have to safely move. Now, think about the imbalances that can occur, because as Maxim said, if in equals out, the level doesn't change. The only time the level changes is if there's a flow imbalance between the in and the out. What is the biggest disturbance or a typical disturbance or flow imbalance that this tank has to fight against? In this case, I like easy math, so we're going to say 2 liters per minute. The worst thing that can happen is a 2 liter per minute change, right? Which doesn't sound like much till you realize it's only a 100-liter tank, right? But if you have 2 liters per minute, you've got 10 liters of space above and beyond, how long does it take those 2 liters per minute to hit a target, right? The math is simple. You've got 10 liters of surge space, you got 2 liter per minute, Divide 10 by 2, you get 5 minutes, which basically means that, hey, if I'm sitting at set point and I get hit with a disturbance and I don't do anything at all, that level will hit a target in 5 minutes, right? That is just kind of a really simple exercise to kind of understand the time scale at which this tank needs to respond, right? So if I have this disturbance and I'm at this set point, I need to make sure my arrest time is at least 5 minutes or smaller, right? Larger than 5 minutes, I could potentially, cross the threshold. So that's kind of how you think about an arrest time. And this math works, this concept works regardless of the objective. If you've got really tight constraints, let's say for a minute that my target is not 60 and 40, right, but 51 and 49%. I've got 1% because, hey, this needs to be really, really tight. That means I have 1 liter above and below. Again, 2 liters per minute, right? 1 divided by 2 means I have 30 seconds to recover from this. So you start to see now, okay, well, this is where the time response comes through. And when you start coming up with what the idea is, hey, I got, a 30-second arrest time that I need to have here. Remember what Maxim said? You can't be more than 10 times or less than 10 times the dead time. So if you go do this exercise and say, hey, I need to have a rest time of 5 seconds, but I got a 20-second dead time, you're never going to be able to solve that problem, right? You're not going to, at least with a PID controller, you're not going to be able to solve that problem. You need to look more advanced. So again, you think through the process, you think through what the objective is, you try to understand the dynamics, right? And that will actually kind of help you design this arrest time, right? And this arrest time, this is everything. And if you go to the next slide, Vera. So the arrest time in IMC tuning or lambda approaches is essentially the closed loop time constant for a disturbance, right? So you can see in the trend there, the time it takes for that curve to turn is tau c, which is called the closed loop time constant for IMC style tuning. It's the same thing as the arrest time. So the arrest time is the time it takes to turn. So you've now defined what you want your closed loop time constant to be. If you look at the bottom of the slide here, there's some equations. These are actually how you back into the tuning values, right? So if you know your integrator gain and dead time, and you know what your desired arrest time is, you now have set the objective, you've got the understanding of the dynamics, now you've got tuning parameters that'll give you precisely the arrest time that you're after. And there's a couple of really interesting kind of tricks here. And one of them is around this reset time. And this is probably the least understood component when it comes to level control. Most level controllers, the reset time is way too fast, right? You may not want a 30-second reset time on a level controller. It may be in the 5 to 8 to 12 minutes, depending on what the objective is. Because if you look at what that reset time represents, it's 2 times the closed loop time constant plus the dead time. And so if you think through the idea of the dead times for level loops generally are on the smaller side, right? They could be 5, 10, 20 seconds, right? Time constants, on the other hand, could be a little bit larger, right? Maybe 5 minutes or 2 minutes. In our exercise, it was 5 minutes. Look at what the reset time is. 2 times your closed loop time constant plus your dead time. So if I need a 5-minute arrest time, that means that my reset time is 2 times that at a minimum, right? Plus whatever the dead time is. So it immediately tells me, hey, if I need a 5-minute arrest time, my reset time is going to be at least 10 minutes, right? If I need a 30-second arrest time, my reset time is going to be around a minute, right? So it immediately starts to help you understand and determine, is my reset time anywhere even close to where it needs to be, right? And then of course you do need a suitable gain, right? It's not just, hey, use a 1 every time, right? Sometimes it's going to be big, right? It could be a 4 to an 8. In fact, most level controllers are going to have large gains, right? Very large gains and very little integral action, which means very large reset times or very small integral gains, right? So, these approaches are designed to take the dynamics of a process, take the objective of the process, and generate tunings. There's not trial and error involved, right? It is designing the controller to perform a very specific task. And that's what, using these approaches is going to do for you, right? It's going to remove the trial and error side. It's going to just be systematic. You're going to get the objective that you need based off of the design of the process, the dynamics of the process, and the response. So This is kind of the basic approach to understanding tuning parameters. And if you go to the last, this next slide here, Vera, I could probably talk 2 hours on this slide because it's about the dynamics of a level controller. And there's a couple of things I want to point out. That tuning map that you see on there is basically the impact of reset time and proportional gain or controller gain, right? So moving up is more controller gain. Moving to the left on your screen is going to be faster reset, which means more integral action. What I want you to realize is that all of them overshoot, right? So every time you make a set point change, your levels tend to want to overshoot. I'm not going to get into the reasons why, but it has to do with the integrating nature and integral action, just kind of a part of the nature of it. But notice the instability of them, right? If you start to have a gain that is way too large, you get oscillations. If you have a reset time that is too fast, right, you're going to get oscillations. What's interesting, and this is where a lot of people fall into the problem, if you look in the lower left-hand corner where your gain is really, really small and you've got a fast reset, you have an even bigger oscillation, right? So even though your reset is fast, decreasing the integral gain, or sorry, decreasing the proportional gain is not going to remove that oscillation. It's actually going to make the oscillation worse. So oscillations can occur in level controllers because the gains are too small. And that is completely counter to what you're used to on flows and temperatures. You see an oscillation, you just start having the gain, and eventually the controller becomes dead enough that the oscillations go away. In level, it doesn't happen that way. The lower you make your gain, the oscillations can actually become more prevalent. And so a gain that's too small can cause oscillations. A gain that's too large can cause oscillations. There's really kind of a Goldilocks zone for what your gain should be to get the appropriate response. And usually people put in too fast reset times and they try to compensate with a slow gain, and you end up with a very unstable style level controller. You know, from the standpoint of kind of the different applications in the real world, Vera, if you want to go to the next slide, Maxim's going to talk through some of the other challenges and issues that level controllers can crop up with.
Yeah, thank you, Bob. So I'll cover different aspects and different mistakes and put kind of warning side for you, right? So let's talk about the tuning. So we learn if we want to be slow or fast, right? So let's talk about overtuning. Overtuning is mean like I push too much, right? So you may meet your objective. Okay, if let's say you want a fast response and you push your overtuning, but it may create issues. So you may look at other aspect than just the level itself, because the control element may work too much, right? So you may be really tight on your set point, but you may have too much. So if your valve or your equipment are working too much, you will have more wear and tear, more maintenance, and maybe change, fail, and eventually failure. You can add to that like energy consumption to move this. And again, if you open your vision of not just the level, overtuning can send disturbance downstream, create oscillation, and then affect the processes, whatever it is about quality issue. Undertuning as well, like kind of reverse or effects. If you're too slow, then you may miss your mark. You talk about the RS times. If you were too slow, then you will go over, maybe spill, you may go under, may trip the pump, so you have to stop. And all of this also, as he just showed, like if the gain is too slow, it will be oscillatory. It may be oscillatory, so oscillatory in the level, but also downstream affect your quality. So this is for your tuning. So be careful and look upstream and downstream of your processes when you pick your tuning. Choosing the tuning is one thing, but not understanding the equipment or the valve and the sensor that you're working on would be a mistake as well. So if we stick with the valve itself, we already mentioned that some of the valves are nonlinear, right? So you did your model, you calculated perfectly, but you were moving your valve in the, let's say, the 10 to 30% range. But then in real life application, you're really more working in the 70, 80, 90 opening range, which may have a total different response, which will change your dynamics. So when you do your model in the area where you're gonna be operating. There's sometimes it's valve some positioner have internal deadband program. So you want to be precise, but they will move only after 1% or so. It will affect your response or your accuracy that you want. You're using VFDs. VFDs may have ramps. They cannot move maybe as fast as you want. So your controller needs to respect that. If you go in the sensor itself, so you're measuring levels. So there's different technologies, DP cell, differential pressure, radar, ultrasonic, load cell. So understanding the technology that's measuring, the noise that it has, is it filtered? Do you have the right technology? Or you affect by foaming and so on? Will of course affect, because whatever you measure is what you need to control. And sometimes internal filtering, it may look good because it's super stable, it's not noisy, it adds delay, and we already said delay is basically your maximum speed. So if you're adding delay, may not be what you want. So valve, that sensor dynamic is good as well. And then when you do your objective, make sure you understand your processes and your objective. What's upstream, what's downstream? Do I need to be fast, slow, or disturbance rejection? And as Bob said, be careful. We show you the formula, but sometimes the integral is the gain is too much. You have too much integral, so meaning the number is small, so it wants to integrate. It's already integrating process, so it will cause the different issue as well. So not just the P and I, there's a little bit more going on. So look broader to understand and choose the right tuning.
Mm-hmm. Tuning is always the last thing that you do, right? You look at the whole application, you look at the instrumentation, the system. Then if all of that checks out, then you can tune it, right? And so Vera, if you want to pop over to the next slide. There's lots of different level control applications out there that we've kind of talked about. And, we're going to talk a little bit about kind of cascade level control here for about 2 minutes, because that's all we get. But, that we're going to do our best. There's lots of great applications out there. And if you think about, 3-element control of a drum level, you talk about filler applications for bottling lines and stuff like that. These are applications where cascade control works out pretty well. And it really comes down to, what are the control objectives that you're trying to deal with. And unfortunately, we don't have time to go into 3-element control and feed forward control and all that stuff. But there are some really advanced applications that you can do around level control to improve performance. Cascade's one that Maxim's going to talk about here in just a moment. Feed forward's another. Adaptive control is another one. Adaptive control and level is kind of an interesting idea, is that, under most conditions, like something like a gap controller can actually be very, very useful. You're within, 5 or 10% around set point, be very, very conservative, nice and slow. But as you move maybe 10 or 15% away from set point, you can, increase the aggressiveness of the controllers, be able to recover and then move back in. So you're not always aggressive, you're only aggressive when you're far away. So something like a gap controller, which basically makes the controller gains more aggressive when you're outside of a band, would be a good approach. Cascade's another one, feed forward is another one. And it really comes down to, you start applying these different strategies like cascade and feed forward and adaptive when tighter control or safety is really important, especially things like steam drums, right? You don't want to trip a boiler, because that's not only just a safety thing, that's a production thing, right? If you knock a boiler offline and you don't have a backup out there immediately, you could knock a whole area or a unit down. So making sure that you've got the right applications, the right strategies in place to be able to deal with all the different scenarios. So Maxim, if you want to go ahead and take the next slide here on Cascade. Sure. I'm sure we've left you 2 minutes to cover all of Cascade, right?
Yeah, no, it's a simple Cascade application, right? So let's start with the graphic in the middle, the bottom middle, right? So we want to maintain the level inside this tank. So there's an exit flow. So there's a client drawing water from this, and you can see that my level control, the LC, is looking at measurement of the level. In this case, look like a pressure cell. So I know the level, and what I want to do is I'm asking this valve to add or remove flow. It's pretty simple, right? It's pretty intuitive. So if the level goes down, I will say, well, open the valve, give me more water. The issue in those types of control is that, well, we're drawing water from a header. that has other clients, okay? So in this situation, let's assume that the pressure is not that great. Some clients takes a lot of water, so the pressure drops. So what's gonna happen to me is that, let's say my valve is open 50%. If the pressure gets higher, well, I get more flow, so the level might increase. But if the pressure drops, then I will get less flow. So in those situations, then what's going to happen? Let's say I have less flow. The pressure is dropped. I have less flow, so the level starts dropping. I measure it, and I say, well, open the valve. But I'm reactive, right? So the level needs to move away from set point for me to measure it, and then ask for a different position. So I'm subjected to all this instability. The solution is to have what we have on the right side, what we have a cascade controller. Cascade controller, what it does is that the level controller is not asking a valve position. It's asking a flow set point. That's why you have this FC. So you're measuring the flow that you're adding. So you have what we call first the inner loop, the FC itself. So measuring the flow and moving the valve. So if the pressure change, it goes up or down, it doesn't matter because I'm measuring how much flow I'm adding to it. So the inner loop, which is the flow loop, which needs to be set fast. So we want a fast response here to absorb all those changes. So I always have a constant flow. The pressure goes up, pressure go down, doesn't matter. I'm adding the same amount of flow. And if you go with what we call the outer loop, the level controller, it's still looking at its level, and now it will tell it, well, give me that many cubic meter per hour, that many liters per second, whatever the measurement it is, but it will look at a broader picture and say, give me more flow or less flow, instead of being subjected to the change of the pressure. So those setup where we have the flow loop with absorbs and control all the change in the pressure, fast controller, and then we have a slower controller, which may our other loop just look at the level and ask a different flow. So these architecture are way more stable. So you will have a better control on your level because of those types of control. So this can do many cascades, but this is one simple application that really helps in those types of situation. And I think we have one more question. Yes.
Yeah, we have one more poll, and yeah, it's in your screen, but I will start with the questions too. Once they are, you are all answering the poll here, the question, I will start. So Maxim and Bob, what is the best approach for integrating process unit, like an evaporator set? Should the first tank in series be tuned, then go down in line? If not, this done carefully, downstream level control will incur oscillation from loop response of the first tank.
Yeah, I mean, there's definitely lots of approaches to decouple controllers. Easiest is probably through just the tuning parameters themselves, right? You don't want them all to have kind of the same response time. If they have the same response time, there's some fighting that can take place. And so you tend to kind of stagger those responses down. There's also feed forward or decoupling style algorithms that you can use that use the output of the upstream level controller as an input as a disturbance to the downstream. And so you can use that as kind of a decoupler, almost like a single direction decoupler between level controllers. It somewhat kind of depends on, is the disturbance only in one direction? Is there recycle effects? Is there other things? But there are some strategies. Maxim, what other approaches?
Yeah, I think you covered them all. So Bob talked about RS time or time closed loop, right? So when we talk about decoupling, is like, depending on the scenario, you may want to have one that is faster, so it will react faster, and one is slower. So understanding your processes, you will choose, okay, well, this one is my fast one, so this one will react faster, but this one will be the slower one. When we have the processes that are kind of cascade one in another, right? I talk about flotation cells in the mining industry. So usually a flotation cell is not a one cell. So the first one, when it controls the level, it sends flows to the next one. So the next one will see the water go, and you like at least four, let's say 4 or 5 cascading. So the idea that Bob says in this case, so if I the first cell sends flow downstream, either way the second cell should also already release some flow, and we use the feed forward. Feed forward is saying, well, if I move my valve by 10%, like the next one will move it by 8. Let's say it's never really a full one-on-one reaction. So they move at the same time. So why we use that instead of the first cell that sends flow in the second one, instead of the second one to see the disturbance, so it goes up and then I need to, it's late to react and then we have a disturbance. It tries to match the response that it should have right away. So we measure it and then it matches it. So that's usually so decoupling and then feed forward is usually good tools to solve different interacting processes like that together.
Perfect, thank you. So second question, can most level controls be tuned through first principles if the volume and flow rates are known, the drain, field dynamics are known, and tuning can be calculated prior to commissioning?
It's interesting. So that integrator gain can actually be directly calculated off of first principles. So you can actually back into what an integrator gain is if you know the size of the pump and how much flow that it draws in and out for each percent. You know the volume of the tank. You know the cross section, the geometry. You can back into the integrator gain. The dead time is more of an installed characteristic, right? You won't really know what the dead time is. You could probably have some estimates. I know how long the pipe is. I know what this is and that is. You could probably get close to it, but that's going to be much more of an installed characteristic versus something that's maybe first principles. But you can definitely back into that integrator gain if you know all of that first principles information to it.
Yeah,
Okay.
totally agree. And if you're, so we say tune for the worst case. So if you have some doubts, so you could guess the integrality, the dead time of your processes. So if you're not sure, I will say, let's say between, let's say 30 or 30 seconds, and use 30 seconds. It will yield you more conservative tuning and should cause less trouble. So usually when we, because we do that for plants, we had an example where we pre-tuned 200 loops, right? So we didn't know all the dynamics. Some of them we could calculate, but we kind of set them on the safe side, so they were able to start with loops that doesn't cause problem. And usually a slower loop will cause less problem than one is, it's sending oscillation, right? So that's kind of our starting points during ramp up and commissioning. At least you have something that's somewhat stable, and then you can push and then really make your model and do the tuning just like we did with the different objective.
We are running out of time, and we have quite a few questions here. If we don't have the time to answer your questions during the webinar, we will send the answer. We will start talking to you by email. So don't worry, all the questions will be answered. We have one more here that I think we have time. So how can I know if it's worth the cost to add in instrumentation for a cascade level control?
If you need tighter control, right? I mean, that's where it comes down to is level. If it has to directly manipulate a valve, all of the dynamics for the valve have to be dealt with the level controller, and it's not very good at dealing with hysteresis, backlash, stiction, changes in pressure fluctuations, right? So some of the examples that we went through, the big disturbances, if the valve position is in a perfect relationship with flow, where hey, 40% valve position is always 50 liters per minute and 50% is always 60 liters per minute. If that relationship is not true, Cascade will always improve the performance, right? You're going to get better because you're going to linearize the dynamic from the level controller. So you can generally, get much better performance out of Cascade controllers on level control from maintaining tight. The disturbances are dealt with upstream, and so you can get improved performance. What the impact is on the process depends on the process, right? We did a Cascade control on filler systems on a packaging line, and it was I think it was like a 4% improvement on rejects, right? That's a significant amount of rejects that were we removed by adding a Cascade loop, and so the value was there.
Yeah, I think that's good. And the I think the initial question is like, is the word adding a flow meter? I think I'm not sure if that was the premise of it, right? So I would say if you have it already, just go with the cascade. I think you will have improvement. If it's already in there, there's no cost, right? It's just tuning properly. And otherwise, it's iterative approach. As Bob said, let's say it's not there, the flow meter, you cannot do cascade, you will reach your limit. And now we showed you what's your limit based on the response. You will see the disturbance. If it's not enough, then it's worth, seeing, well, what am I gaining with adding my flow meter? And then I will program my cascade. And then if cascade is not enough, then there's feed forward, and if feeds forward is not enough, there's model predictive control, and then you can go on and on. But usually we go with the iterative. So what we have, maximize it, optimize it, understand the behavior, and then you will see what your limitations are. And if you want to go further, then at least you will be able to justify and understand, what I'm missing and how to go get the extra gains and performance.
Thank you very much, Bob and Maxine. I think it was really good. We received a lot of questions. As I said, we will read by email to answer them all. And I hope you have all a great week, a great Tuesday. Okay? Thank you.
Absolutely.
Thank
Thanks,
you very much.
everyone.